Finally, here in example 5, we're looking at a cylindrical object that has a circular cross section with a radius of 4. We're going to place a spherical marble whose radius could be between 0 and 4 into the bottom of the pot. We want to know what is the radius of the marble that is going to require the most water to cover it completely. Presuming the marble does not float, we have to prove our assertions analytically. Okay, so the first thing that we're going to try to do is draw a diagram of the situation. So I've got a cylinder, and inside this cylinder we have a marble. I know that the radius of the cylinder is 4. I know that the radius of the marble is between 0 and 4, so 0 being there's no marble, 4 being that it touches both sides. So I'm not sure how big my marble is yet. It's just in between there somewhere. And we will also assume that the water level is going to be exactly equal to the top. We're not going to drown the marble. We just want to put the most water that can cover completely, not too much water. We want to just have a little bit of water filling in around this marble. So if I have 0 marble, there's obviously 0 water. So what's the radius that's going to require the most water to cover it? Okay, so that gives us a little bit of a diagram. Let's see what we can do here to flesh this idea out. Okay, so the first couple things that we want to think about is for our objectives, we need to compute a formula for the most water. And so since the water is going to be filling space, we're going to be looking for some kind of volume situation there. Okay. So if we start, before we even write my objective function, I'm going to start with what I know about volume for each of these shapes. So for the cylinder, we know that the volume is pi r squared h, and for a sphere, volume is 4/3 pi r cubed. Now, we do need to be careful that we make sure to consider the r's here separate, so they're not the same r, because the cylinder has a fixed r and the sphere does not. So we have, say, r sub c and r sub s, just making sure that they're not the same r. There's no reason to think that they would be the same r, so they're two different variables right there. All right. So the volume of the water is going to be the volume of the cylinder minus the volume of the water, and that's how we're going to build our objective function. So in step 2, when I go for that volume, so the volume of the water is going to be the volume of the cylinder minus the volume of the sphere. So we'll just call it V as I start writing, but then we will put together those two pieces. So the volume of the cylinder is going to be pi times, I do know the radius of the cylinder, and that is fixed, so we can do pi times 4 squared times h minus the volume of the sphere, which is going to be 4/3 pi times r cubed. That way I won't need subscripts if I go ahead and put my rc in there right away. Okay, too many variables. I do have r and h, so I'm going to want to relate at least one of those in terms of the other. Let's see what we can do. So the first thing that comes to mind is that the diameter of my sphere should match the height of that water. So the height of my water is going to be twice the radius of the sphere. So then I can put twice the radius in here, and since I already have 4 squared is 16, 16 times 2 is going to give us 32 pi times r minus the 4/3 pi r cubed. Okay, so I forgot to label some of my steps, so I'll go back and do that. That's step 3, getting in a constraint function, and then this is actually step 4 right here, as I use my constraint function to substitute into my objective function and rewrite my objective now as a function, this time in terms of r. So I have v of r. All right, so we've got the original objective function a constraint, and then we have rewritten the objective function in a single variable. So that was, I guess I had step 1. I drew a picture. Steps 1 through 4 right there. Step 5 is going to ask us to find the interval of interest. In this case, it's going to be the smallest that r can be and the largest that r can be. I already actually know the smallest that r can be and the largest that r can be, both in terms of the diagram and because I was told, because the marble is going to be moving. Smallest is no marble, of course, so 0, and largest is going to reach the edges of the pot, so 4. So our interval of interest is going to be r between 0 and 4. So it was given to us as well as it makes sense in terms of the context. All right, so that's step 5, and then step 6 is going to be getting our derivative. So we'll do v prime of r is, so I have 32 pi minus 4 pi r squared. And then step 7, we're going to be looking for places where the first derivative equals 0, and where it doesn't exist, we're looking for our first order criticals. This is polynomial, so there are no places where it fails to exist. Just don't forget to look for them in case it's not polynomial sometime. But equals to 0 is going to give us 32 pi minus 4 pi r squared equals 0. So let's see, we've got 32 pi equals 4 pi r squared. If I divide off the pi, that's, okay, then 32 divided by 4 is 8 equals r squared. So plus and minus 2 square root of 2 for r, but we're going to select the positive one, of course, because in a real object we wouldn't want to see a negative radius, and also it's not in our restricted domain. So in our domain we have one critical value, one first order critical value. All right, now that I have step 7 complete, we're ready to go on to step 8, and we get to choose a test. Let's choose the second derivative test just for fun. That's the one we did first, so it's been a little minute since we've done that. And the second derivative is actually easy to compute right here, so it's not going to be difficult to use that test. So the second derivative is negative 8 pi times r, and if I evaluate the second derivative at 2 square root of 2, I get negative 8 pi times 2 square root of 2, so I get a negative value. Since I have a negative value, that means that we are concave downward at our critical, and that means that we're going to be a maximum. So our conclusion is that we have a maximum at r, I almost wrote an x there, so at r equals 2 square root of 2. Well, that's luckily what we were looking for. Remember, we're trying to find most water, so that's going to be the maximum. So now we're ready for step 9, just getting our conclusions and verifying that they make sense from there. All right, so in step 9, we have that a radius of 2 square root of 2 centimeters will require the most water and then let's tell how much water it actually is. So back up to our volume function. We had up here the original volume function. If we evaluate that at 2 square root of 2, so volume of 2 square root of 2 gives us 32 pi times 2 square root of 2 minus 4/3 pi times 2 square root of 2 cubed. So 64 pi times the square root of 2, and then let's see, this is 4 pi thirds times, if I cube 2 square root of 2, that's going to be 8 times 2 is 16 square root of 2. So 64 pi square root of 2 minus 64 pi square root of 2 over 3, getting a common denominator on that ought to give us 64 times 3 minus 64 should be 128 pi square root of 2 over 3 cubic centimeters. So back down to my conclusion. The radius of 2 square root of 2 centimeters will require the most water of 128 pi squared of 2 over 3 cubic centimeters of water.